Okay, thank you very much for this kind introduction, Boda, and thank you everybody for having me at this interesting workshop. Certainly, I wish it was in person, and I totally agree with Tilman Pfau, who said that these workshops live off the fact that you meet people and you talk directly. This is not possible, unfortunately, and I know how the situation is in India right now. Here in Austria, it's a bit better now. In fact, we are talking about a lot of relaxations already starting next week in view of all the vaccination going on here. Anyways, yeah, so feel free to interrupt me then at 20 minutes or 25 minutes and for all the questions. I will actually start with a rather broad introduction, and I think the real interesting things only come later, yeah, and in my second lecture. So, as you can see from the title of my talk, I will be focusing on molecules and in fact on molecules at ultra low temperatures. And in this series, in the school, as you know, we will have also other prominent speakers that will continue this and tell you about their very nice results. So, but before I start, let me briefly tell you where Innsbruck is. Perhaps some of you are not aware of that. First of all, Innsbruck is in Austria. So Austria, as you can see here, is sandwiched in Central Europe, sandwiched between Germany to the north and Italy to the south. It's not too far away from Munich and Salzburg. Salzburg, as you know, the hometown of Mozart, for example. Munich is famous in science, for example. In the old days, for example, Sommerfeld worked there. Vienna is quite far away. It's on the other side of the country. Sometimes, actually, Munich is really a lot closer, or even Switzerland on the western side. Innsbruck is actually where Austria is very narrow, just 50 kilometers across. So you can almost walk basically on one day from the German border to the Italian border. And Innsbruck is here at this intersection right inside the Alps. It's one of the few cities inside the Alps. And you can see from the picture above here, where you see the river. Actually, it's Innsbruck. It's the bridge across the Inn River. So this is the river, and you see the mountains in the back. And in principle, such a picture here with snow on the mountains, you can have in principle any time of the year. It's unlikely in July and August in the summer, but it can happen anytime. Anyways, it's a natural place to do ultra-cold physics for various reasons. Actually, in Innsbruck, we are very fortunate to have these colleagues in our faculty. In fact, Rainer Blatt, with his ion trapping group and quantum information group, was the one who brought me to Innsbruck a long time ago. I actually later joined Rudi Grimm as an assistant more than 20 years ago, and we were able to set up an old ultra-cold lab with various elements that we were able to condense in Innsbruck for the first time. But I should really highlight Peter Zoller, our theory colleague, who has been very active in the field. And in fact, Peter has been one of the pioneers in quantum optics and related fields, as you probably know. In fact, Peter Zoller and his team, they were the ones who formulated a lot of the very influential proposals in our field, if not in all of recent physics. Let me even say that. Yeah, if you look at how many citations these proposals have gotten, it's actually quite amazing. And some of some of these proposals you probably know, if not all of them. Let me highlight a few. For example, the proposal to use trapped ions for quantum communication. So this was actually the first proposal to propose a realistic gate operation on in this case, on cold trapped ions. And actually that brought me into the field, because it turned out that my advisor, Rainer Blatt, then said, well, this is your PhD topic. You do this. Well, we didn't do it during my PhD. Another seminal proposal a little later was to use cold atoms and optical lattices to study many-body physics, in particular the superfluid to Mott insulator phase transition. And in fact, this is a workhorse in my group. We are using this every day, and it's really important for us. And we are very happy that there has been such a drastic development in our field. Well, then there are other proposals that you probably know about, for example, on dipole blockade, what we just heard from Tilman Pfau. Also here, one of the main proposal came out of Peter Zoller's group. And also, as we will hear about, dipolar gases have been a very prominent topic in the local theory group. But this brings me to actually a proposal that I in particular was fascinated by. I mean, I was fascinated by all of them, but certainly in the lab, you can't do everything. Yeah, you can only run certain things. And this is the proposal from 2002 by Dieter Jaksch, who was, I think at that time, he had just graduated from Peter's group. And he proposed how to create a BEC of molecules by going via atoms and dynamically melting a Mott insulator of atoms. Actually, I'll come back to this later. That's why I already want to bring it up here. And in fact, this proposal fascinated me nearly 20 years ago. And at the moment when I had my own funding, I said, well, I want to do something like this. Yeah, and you will see why I'm so enthusiastic about this and why I like this so much. Yeah, even though this is certainly a very complicated and difficult route that we've been taking there. So, in fact, Peter, with his proposals, certainly opened a lot of research directions. And let me just remind you of what we are talking about, yeah, about some of the basics, yeah. So real materials, and I think it's fair to say that a lot of that, what we are all interested in, you and I, is understanding real materials, yeah, working with real materials, building novel materials, but going into the real world at some point and perhaps building a real quantum computer that is where you perhaps do not need to do laser cooling, yeah. Anyways, so in electrons are our favorite carriers of charge, as you all know. They are easy to transport, as you know, and they show peculiar properties at low temperatures like superconductivity. So these move through the potential of the ionic cores, and that gives rise to many interesting effects that we all love in physics. Yeah, I don't even go into any of the details here, certainly. Yeah, with atoms. Yeah, okay, perhaps say effectively this potential, to a good approximation, looks then sinusoidal, and certainly there are very rich band structure and so on that makes life of a physicist interesting. Yeah. So now in our case, we don't take electrons for obvious reasons, but we take atoms that see a laser standing wave here in the simple situation, just in 1D comic here that I'm drawing here. And our electrons are the atoms. Yeah. So atoms that we laser cool. Yeah, we'll come back to that. And so we emulate the situation of our electrons by creating an optical lattice, a crystal of light, through which our atoms or even molecules perhaps can move or should move. And we'll see very nice results from these colleagues later on, from from Esslinger, Bloch and Esslinger and Martin Zwierlein. Yeah, so Immanuel Bloch and Tilman Esslinger and Martin Zwierlein. So now this is the situation that we are interested in cold atom physics. Yeah, and what do we gain and what do we lose when we do this? Yeah, why do we do this? Yeah, apart from having a lot of fun in the lab and doing textbook type quantum mechanics experiments, I can really say this. I mean, that's what we, and in particular our colleagues, are doing. Yeah. So first of all, the system is greatly magnified. Yeah. So we have optical lattices and not angstrom length scales. So we have the possibility to detect particles individually and also to directly measure the momentum distribution and so on. So there are lots of advantages by this very strong magnification. Then everything is slowed down. Yeah? Atoms are much slower than electrons. The entire dynamics is much slower. And so the advantage is that one can see processes without going into with doing a lot of effort. So for example, we don't need any femtosecond lasers to probe the dynamics of our particles. Yeah, so this is an advantage, but on the other hand, this is also a disadvantage because slow dynamics is related to reduced energy scales, and that means actually very low temperatures. Our Fermi energies, to give you a number, yeah, in the order of microkelvin and not in the Kelvin regime. Yeah, so we need to go to very low temperatures with these atoms, and that's what we call ultra-cold quantum gases. And that's actually only possible because we can laser cool. And even then, we are not really, as you know, in the low temperature regime. Yeah, so this is a drawback to some extent. Yeah, but on the other hand, it turns out that that there are some workarounds. Yeah. And then also a drawback using atoms is that interactions are, at least in most cases, they are local. Yeah. So short-range van der Waals interactions, basically contact type, delta function type interactions. And so we need to do tricks to do to obtain long-range interactions. And Tillman Pfau just told us what to do, what one option certainly, yeah, and but it's evidently not trivial, even though there's a long history of doing, for example, Rydberg systems, as we just heard, but doing Rydberg systems plus many-body physics and plus having all the ingredients that you wish is certainly not easy, yeah. So what platforms are there to solve this problem of missing long-range interactions? Yeah, so actually a very popular platform is by now ions and ion traps. And with ions and ion traps, you can in fact to some extent engineer interactions between the ions. You can actually engineer the decay of the interactions as a function of distance. And so just a disclaimer here, I'm listing some places where people are doing this work. I'm certainly primarily been listing the people that are part of this conference, and there are many more by now. And I hopefully I don't I'm not doing I'm not doing anything bad to anybody. So, and this picture here is actually taken from the Innsbruck group, yeah, and we'll see nice talks what you can do with ions and ion traps later on from our friends Christian Roos and Stefan Village and Didi Leibfried. Now, then there are atoms in cavities, yeah, so interactions mediated by the photons in the cavity, and I think Tillman hasn't put his abstract online, but I'm pretty sure that he will talk about atoms and cavities. And this image is taken from Vladan Vuletic groups and their experiments in various places apart from Zurich, at MIT, Stanford, Hamburg, Berkeley, you name it. Yeah, so that's also an option, and you will see in the school, I'm sure, very nice results on that. So now the next possibility, and Tillman Pfau already mentioned that briefly, that he will be talking about it, is to use dipolar atoms, specifically magnetic dipolar atoms, to use or to make use of long-range interactions. Yeah, so this has been done in Stuttgart, for example, in Tillman's group, and in various other places. Also here in my colleagues' group, Francesca Ferlaino's group, and there are really nice results from various places on dipolar atoms. And finally, this list here is Rydberg atoms, as we just heard about. Here I'm showing an image from the Caltech group with Rydberg atoms trapped in tweezers. We'll hear about that apart from what Tillman already said from Vladan Vuletic, and there are various places where Rydberg atoms are being used. And here I highlighted the ones there where the many-body aspect is sort of the dominant drive. So these are 4 platforms that you all know about, and we'll hear about many of these platforms in this audience, in this school. Yeah, and what else is there apart from other options? Certainly, this list will not be exhaustive. I think I'm just listing my preferences, is also the school's preferences. So it's actually polar molecules. Yeah, polar molecules here take dimer molecules, and it's indicated here, composed of 2 atoms. And these can interact via the electric dipole-dipole interaction in this characteristic way. The pre-constant CDD, with D being an induced dipole moment. You actually polarize the molecules in the lab frame with an external electric field or by applying AC fields. And then the interaction is falls off as R to the 3rd power, and there is an angle dependence. Assuming now here that all the vectors are aligned in the same way, but you can actually now rotate them with some angle. So there is an angle dependence. And we will see very nice results from Juni and Martin Zwierlein later in the school. Yeah. And there are experiments at Gilla, in Innsbruck, at MIT, Durham, and many other places by now. So polar molecules are one platform, one alternative platform. Now I've shown you 5 platforms for playing with long-range interactions, and it's hard to give a preference, but let me just, and certainly all of them have yielded very nice results, and I'm sure will in the future yield further very nice results. Let me just state the advantages of polar molecules. And I see there are questions in the chat. Let me actually do the advantages and then come to have a quick look at the questions. So, so the advantages of polar molecules are, the interaction is relatively strong. Yeah, it's certainly not as strong as what we've just seen from the Rydberg systems, but in comparison to magnetic dipolar atoms, yeah, so ground state atoms, they are comparatively strong, and that's certainly an advantage. Yeah, so one perhaps not in all cases has to go to the very lowest temperatures. In the end, actually, that's what we do or try to do, but perhaps later on this can be relaxed a bit. Yeah. Then this interaction is tunable, yeah, by either by how you polarize your molecules. That's a nice feature. Then there is an angle dependence, as I just mentioned. Then all the control techniques that have been demonstrated on atoms, ultra-cold atoms, can, and I don't see any no-goers here, can be extended to molecules. Yeah, not everything has been demonstrated, but by now I would say a large fraction of these techniques has been demonstrated. Then dipolar molecules are long-lived. Yeah, what do I mean by this? I will come back to that later. But when we just have them, let's say, in a trap and in a lattice, for example, where they collide, we and the community has demonstrated that these molecules live for a very long time, so they don't decay. Yeah, so decay due to black body radiation or so is negligible. So that's for some experiments this is an advantage. Yeah, and then certainly next we have to discuss what happens when these molecules collide, and then perhaps there are relaxation processes and they will effectively kill these molecules. Yeah. And and actually the last sentence here, the last point, brings me to what I think will be the future soon, that one is actually able to form molecular superfluids. So a Bose-Einstein condensate of dipolar molecules with rather strong interactions. As we will hear in this workshop, we'll hear about supersolids and Bose-Einstein condensates of dipolar magnetic atoms, but with rather weak interactions. And we could hopefully be in a regime where interactions are really strong. So an open question I already said at this point is, can we form a Bose-Einstein condensate of molecular dipoles? Yeah, and when I compare to Rydberg atoms, I'm not saying that Rydberg atoms cannot be brought into a state of a superfluid. Who knows? Yeah, I'm very careful here, but for sure it's not easy. Yeah, so perhaps one can do other types of excitations on Rydberg atoms into the state of a BC, but it's not so easy as with dipolar atoms, and I think with dipolar molecules this will be possible. Certainly, there are also challenges, yeah, or difficulties, yeah, if you want to see it on the negative side, but I will call it challenges, yeah. So first of all, molecules are not readily laser coolable, yeah. There are exceptions that I will briefly mention later on. So that the technique of laser cooling cannot be, at least to almost any molecule, cannot be applied. One has to say, on the other hand, with atoms, it's not too much different. Only a handful of atoms can be well laser cooled, and with many others, it doesn't work. Yeah, but certainly the field of molecules is much richer than the field of atoms, and the class of molecules that can be laser cooled is rather narrow, even though they are very nice developments lately. Then the next question is about stability. Yeah, so the field of ultra-cold atoms lives off the fact that ultra-cold atoms are stable. Yeah, so when I talk about stability, certainly I mean systems that are sufficiently dense, interacting systems, and systems that we want to trap and where we want to see interesting interaction effects. And with atoms, it has turned out, yeah, I would say 30 years ago it wasn't clear, but it became clear due to the experiments in the 90s that Bose-Einstein condensates are sufficiently metastable that one can actually produce, so atomic Bose-Einstein condensates can be made in the lab. Then another challenge is connected actually with this is scattering of molecules. Yeah, so what is exactly happening when molecules scatter? And for example, if you had a chemical reaction in the background that can happen, what does that actually? How does that affect your stability? Or even if you don't have that, if per se molecules would be stable under two-body processes, can they still effectively collide inelastically? So this is in fact still over years now has been a debate, and it's not really clear, and we've, I would say, still not really seen the final experiment on that. Yeah, so this is a challenge, and actually it's an interesting challenge. And then finally, molecular preparation strategies are comparatively complicated. Yeah, so we've seen a Tillman-Faust experiment in vapor cells, which are where we can see quantum physics at a very basic level already with rather little infrastructure. Here with molecules, certainly we have to go through quite some effort, at least the way we do it. Yeah. Perhaps we like to do it difficult, yeah, but in a difficult way. Okay, anyways, it's a double species setup, and we detect usually via the atoms, via the molecules. It turns out to be advantageous. So we have to pull all the tricks of cold atom physics plus some additional molecular control tricks to make this thing going. Yeah, so there are challenges. Yeah, and but that keeps us happy that we have challenges. So let me have a quick look at the chat. Okay, I think there's no question relates to me, yeah. So I can actually continue for a moment, yeah. And Borda should interrupt me once there are questions, or we should stop for questions. So now,
so far there is no question.
Yeah, so people should raise their hand or put something in the chat, but we're just at the beginning of my lecture still, certainly, yeah. So, so what is the goal in my group and perhaps in some other groups? Yeah, it's, to prepare samples of molecules that have where the density is such that if you think about a lattice potential, we have something on the order of unity filling. Yeah, so this is sort of the goal, and I'm totally happy if we do this in 2D, yeah, as indicated in this comic. But perhaps we can also do more, do layered system or something else, yeah, or even 3D. And actually, Jun Yi will talk about that surprisingly that molecular dipoles in a dense regime can be also stable in the 3D setting. Yeah. So this is certainly a comic here. This is my dream that I have been dreaming about. And what are the applications? Let me jump ahead a little bit already, yeah, to see what has been my motivation for many years. Yeah. So I'm writing down here some Hamiltonian that most of you probably know, but let me just walk you through this and remind you. So I'm writing down a Bose-Hubbard type Hamiltonian where I'm adding an additional term. Yeah. So what we are up to is to do Bose-Hubbard physics and generalizations of that with dipolar molecules. And I'm writing down, let's say, the simplest Hamiltonian, I think, that you could write down, and you can think about more interesting situations certainly easily. Yeah. So what is this? Yeah. So it actually, you see three terms. Yeah. And usually interesting physics happens when two of these energy scales set by the prefactors J, U0, and U1 here. I'll walk you through what I mean by this in a second, when they become equal. Yeah. So it could even all three can become equal. Yeah. So that's usually the situation. Very, very generic. Yeah. So what is this actually? Yeah. So this Hamiltonian, in the spirit of what Peter's group suggested a long time ago, describes the dynamics of our atoms on a lattice. Yeah. So like electrons in the crystal lattice. So we have the tunneling processes here in the first term, indicated here with this little comic. We have the local interactions, the on-site interactions, and I should already say here that that certainly that includes also the dipole interaction that gives also rise to a local contribution. And so these two first terms that you all know about this have been very rich already, and various groups have played with this now for many years, in particular also our group. Yes. So already these two terms are very interesting, yeah, and it has given to rich physics. And now we want to add a term that's a next neighbor interaction. So these brackets actually indicate, as here on the left, that this is interaction I and J are the sites next neighbor. So not on sites, but the neighboring sites. And there's an energy scale related to that. And in fact, it turns out for molecules, dipolar molecules, this is actually a rather large number given the typical temperatures in such systems. Yeah. So there's a nice review on all this beyond Bose-Hubbard physics or beyond the standard two terms physics. And in fact, in Innsbruck, there has been an experiment in Francesca Ferleino's group already a few years ago, seeing first indications with magnetic dipoles of this third term, sort of, yeah, in a nutshell. Okay, so this is our motivation, and what actually is possible with this Hamiltonian, yeah. And there's certainly there's been a long history and various proposals what one can do, and one can do at the characteristic phase diagram and the so-called mod lobes in under such a setting, yeah, where you have a non-zero the nearest neighbor interaction. And here this diagram shows is plotted as a function of the chemical potential and the tunneling rate for fixed U1. And the outside area is the standard superfluid in the lattice. And then one can have half filling, a third filling, and quarter filling, for example. So interesting many-body phases, even though this is just a static setting, that go beyond what we know from contact interactions. Yeah. Unless you do some tricks, yeah, with fermions and higher order processes, but and very low temperature. So the dipolar interaction makes this phase diagram more interesting. And in fact, we'll hear a bit about this also in this workshop, is that there are new phases sandwiched in between. SS stands for a super solid phase, a lattice super solid, where we sort of combine superfluid properties with non-trivial correlations, spatial correlations. Okay, so this is one motivation for doing this. Yeah. Let me give you just two others, just that you know. Actually, they're totally different in spirit. Yeah. One is in fact indicated here on the right, and just took the picture from one of these publications. It's shown dipoles on a lattice, frozen on the lattice, so no motional degrees possible. Yeah. So in principle, you could do this also with other platforms. Let's say the Rydberg platform. But that's for sure a very nice possibility. We have to talk about what would be the spin. Yeah, we have rotational degrees of freedom, for example, in molecules, and then you have some spin-spin interaction that is sizable from one side to the other. Yeah, so I'm listing here some of the relevant literature on that. And in fact, in Juni's group, there have already been some experiments along these lines. So that's what we could call frozen spins. Admittedly, I have to say, I think the interesting part is where we have everything. We have spin degrees of freedom and we have motional degrees of freedom. I think that takes us closer to real electronic systems that in the end we are interested in. And then a bit more perhaps exotic are systems indicated here, where you have layered systems, where then you can have interaction from one layer to the other, and where where you can form, for example, interesting strings that bind or unbind, depending in this case on the distance between the layers. But it could just be that you modulate the interaction strength, and you then see phase transitions between strings and melting of this string phase. Okay, so there are proposals, for example, by the theory group in Stuttgart from Hans-Peter Büchel. So this is interesting physics, and I think one could give an entire lecture about all this. I'm an experimentalist, so I won't do this certainly. Yeah. So, but just one more motivation. So if you had a 2D system like that with spins like this, yeah, and already what I'm fascinated by is the fact that you could, in principle, do local control, yeah, local flipping on this of the spin here, and then look at how this excitation propagates in your system. Yeah, so something which is very hard with electrons to do, what with molecular dipoles one can do this, or actually with the Rydberg platform, I think there's also a good chance. Yeah, but again, it would be interesting to have also the motional degrees available. Yeah, so this is a bit similar to what you could do in a 2D ion trap, for example, or with at some point. Yeah, it's not been demonstrated yet. That this could be done, or with a Rydberg system. Yeah, and I think 100 by 100 particles are realistic in these various platforms. Yeah, so I call this a molecular quantum simulator. Yeah, so now comes the main question: how do you prepare such a system? Yeah, how do you go about? Yeah, and the trick that we've been trying to look at is actually or what they've been using is to do all the control on the atoms. Yeah, so we have molecules that are actually dimer molecules. They're made out of 2 atoms, and we do all the laser cooling, all the entropy removal on the atoms, and afterwards only quote unquote maintain phase space density. Yeah, so that's the idea, and in fact, a big advantage when you do all the control initially on the atoms, and I'll go into more detail certainly a little later, that you inherit the control over the external and internal degrees of freedom, including hyperfine degrees of freedom from the atoms. Yeah, so we know very well how to do this on atoms. Can we map that onto our molecular sample? Yeah, so then you can ask, why not differently? Why not laser cool, direct cooling techniques? Why not use something else, dipolar atoms or Rydbergs? Well, I gave some answers already partially, and later on some of these things will become clear. Yeah, but I think you see already my motivation why we want to do this on molecular dipoles. So just for the history, this activity started getting serious more than 10 years ago here with this work from Juni's group at Gilla with KRB molecules. And in Innsbruck, we have been working primarily with rubidium-cesium molecule, and then other groups stepped in. And I think this is a really nice and friendly competition. Durham, MIT, Hong Kong, and other places, yeah, Hanover and so on, Munich and so on. So This is still my introduction. Yeah, I'm still doing introduction, but I think I have a two hours, and tomorrow 2 hours, so I think that's fine. So, what is the strategy that we're using in Innsbruck? Yeah, so the idea is to mix two Bose-Einstein condensates. Yeah, so we have very cold samples with very high control, and somehow we mix them. Yeah, somehow. I say somehow because that's the difficult part, and I will emphasize that again. Yeah, and we've been working on this for quite some time. And then we create molecules, yeah, and ensure somehow that the phase-space density remains high, that we don't lose phase-space density, and this control of the molecules, actually, we take all the way to the very ground state of the molecules into a suitable row vibrational state. Ideally, it's the very ground state for reasons of stability, evidently. Yeah. So that's and also because that's where usually the molecules have a sizable dipole moment. So that's sort of in two sentences what we do. Yeah. And in fact, let me bring this, come back to why I actually highlighted Peter Zolle at the beginning. Well, one reason was because he and his group came up with this proposal of controlling atomic samples and turning atomic samples into molecular samples in the regime of quantum degeneracy. So this is this proposal, yeah. So so basically the idea is to do this with a lattice, yeah. A lattice helps in various ways. So the plan is to put both samples into a three-dimensional lattice and to freeze out the motion. So turn actually these atomic samples into a Mott insulating state. So a Mott insulating state with two different species, yeah. And so I come back to this in a second. This is the hard part, yeah. I already say it now, yeah. So going from 1 to 2 is sort of the magic. That's where the difficulties really arise, yeah. Turning these two Bose-Einstein condensates in a sample of dimer, of pairs, yeah, at first. Not even dimers, just atom pairs, yeah. So we want to create atom pairs at each side, ideally with unity filling, and then turn these atom pairs into more bound pairs that are actually a molecule, yeah, weakly bound molecules, and then turn these molecules into ground state molecules where then they can interact when you turn on the dipole. Yeah, so indicated here by my flashing, my flashes, that now these dipoles can interact and do something, can do interesting physics. Okay, so let me actually look at the chat for a second. Yeah, I see there's a question.
Yes, Krista, there is a question. So that is why didn't you consider the chemical potential term in the Hubbard Hamiltonian?
Because I'm keeping it simple. I'm certainly doing it simple right now. Yes, so certainly you should write down more than that. But I'm just wanting to highlight the essence. Yeah, what I would find the essence of the Hamiltonian. Yeah.
So there's another point. This is just a remark. So so the talk is like 1.5 hours today and 1.5 hours tomorrow. It's not 2 hours.
Exactly. Yeah, 1.5. Yeah, when I say an hour, 45 hours, say for 45 minutes. No, that's fine. Yeah, that's fine. Yeah. So now I think I have finished 45 minutes at this point, right? Almost. Is that correct?
Yeah.
A little less. Yeah.
Yeah,
after your lengthy introduction. Or too long. I would have just said Christoph from Innsbruck is now starting. Yeah. Okay, good. So let me continue here. Yeah, still my introduction. I'm still doing introduction, but that was the goal. Yeah, to do a broad introduction. Yeah. So let me see if it doesn't work at the moment. Now, so this step 2 to step 3. This is what we call Feshbach association for obvious reasons. You'll see later. I think this is actually we know how to do quite well. Yeah, with very high efficiency, and it's not pushed to the very limits. Yeah, when I call all these processes that I'm writing down here, we want to do this because we've done all the cooling initially. We want to do everything ideally with nearly 100%. Yeah. And as long as limited certainly by what quantum mechanics allows us, yeah. But that's probably, my guess is it's close to 100% in a at least in a certain setting. Yeah. So this we know how to do with very high probability, and you'll see data later from my lab, and also from Juni's lab. Yeah. So this works nicely, the ground state transfer also works nicely. Yeah. This transfer from weakly bound molecules to ground state molecules. Yeah, where then you can switch on the dipole. Yeah, so this is actually done with a laser technique that's well known. It's been used in the field of molecular physics the other way around typically, but we're using it in the setting of cold atoms, from threshold to the ground state. Okay, and so the bottleneck actually is this first step from 1 to 2. Yeah, and I will towards not today. But tomorrow then discuss this a bit more, yeah, this bottleneck, yeah. But I can already say what is the trick, yeah, that actually we worked on. And perhaps sometimes you don't need to do this trick, yeah, I'm a little bit careful here, yeah. But for the bosons, as we find, we need to pull some trick. And Giller solved this problem by mixing a Mott insulator for the bosons and a band insulator for the fermions. And in our case, with rubidium cesium, where both are bosons, actually we used sort of both double Mott insulator, sort of. I have to be a bit careful, yeah, because we never did this in a perfect way, yeah. So, but that's, and in fact, I can say this already now, that's what we are still working on to optimize this, yeah. So what are the challenges, yeah, for all this, yeah? So the challenges are how to mix the two species, yeah, and we'll come back to that, yeah. In particular, both are bosons, and fermions tend to help, I would say, because fermions, the way they repel each other by the exclusion principle, it usually leads to more stability. I think one can fairly say that, yeah. So then three-body processes are actually a problem, yeah. Also here the fermions might help. But if you have only bosons, you fully run into three-body processes, and you have to be either a bit lucky or do some tricks, yeah, to avoid them. Yeah, and in fact, I have to say we have not yet been able to fully avoid them, and but I think we know in principle how to avoid them. So in fact, as you all know, probably, and actually I will talk about three-body processes a little later in the second hour. Three-body processes are the first is the central processes that make our cold atom samples unstable. Yeah. So two-body processes we can inelastic two-body processes we can suppress by going to the right states, but three-body processes can be a nuisance. Yeah. You can also make them to good use, but in most cases we would like not to have them. Yeah. Yeah, and then that connects actually with the next sentence. Yeah, to suppress inelastic molecular scattering. Yeah, so turns out that most likely that molecular loss is due to an effective three-body process. Yeah, so I'll come back to that briefly later. Yeah, and then the final challenge, which is I think more on the technical side, is how to combine high-resolution imaging as shown down here, where you have your sample and you want to put on a CCD camera and then detect the local correlations, yeah, as indicated here on the right in my comic, to combine that with electric field control. Yeah, so you want to be close with the lens, but on the other hand, you have to apply voltages that are not negligible to polarize the molecules, and it's on the order of several kilovolts per centimeter. It depends a bit on the species of choice of the molecule of choice. So that's actually not trivial. We are working on that, and we still have not implemented the final version of what we want in the lab. Yeah, I have to say that. Yeah, we'll hear a bit more from June, I guess tomorrow or the day after tomorrow, June, but also there's now not yet both. Yeah, the control plus the imaging of individual molecules that's not yet been implemented. Yeah. So okay, that brings me to the outline. This introduction, I hope it was not too simple, but I think it's good to start very gentle, is brings me to the outline of my talk. I will talk about a bit about scattering, remind you of scattering. So I'm the first one in this series to talk about scattering, I think, yeah. And so I think I can take the luxury to talk about a little bit about one of the important tools in our field, that's Flashback resonances. Yeah, so actually I'm making a living of Flashback resonances, essentially. Yeah, I'm using them for making molecules, and I'm using them for tuning interactions. And then I will divert a little bit, I hope you allow this, to talk about three-body physics and Efimov states. Well, this one always has to keep in mind, because that's in the end what limits us, because the rates are sizable, and if you're unlucky, Efimov states can actually greatly enhance the three-body loss rates. Yeah, so I think for most of the experiments, we want to stay away from any of these so-called Efimov resonances. And then I will talk to the subject of this lecture, to the dimer molecules, first to Flashback molecules, then how we go to the ground state. I will divert shortly to talk about homonuclear experiments that have been done in my lab, where we've learned a lot, and then how we do this control on rubidium cesium, and how we are trying to improve this kind of control. Okay, I'm looking at the chat now. I'm seeing a question.
Yes,
okay, what is typically the size of the 3D optical lattice? That's an easy question. Yeah, typically we have in my group we have about 50 by 50 lattice size, 50 by 50 by 50 lattice sites typically. Yeah, perhaps a bit more. I think one can do more. Yeah, I think what one has to do is one has to combine lattices with box traps, and it's been on the agenda in my group. The problem being, perhaps I should say that when you have a lattice, that you also, due to the finite size, lateral size of the laser beams, there is always some weak but non-negligible confinement laterally, and that shifts everything. Yeah, it shifts the entire energies through space, and that's sometimes not very advantageous. Yeah, so but I think we can do systems. I mean, the community. We will be able to do systems with tens of thousands of particles in the end. Yeah, with in 2D. Yeah, that's my guess. Yeah, at some point. Yeah, so 100 by 100 I think is very, very much doable, and if we work a bit harder and we can do larger samples, so that could be tens of thousands of 2D, and then the next question is what can we do in 3D, perhaps even more. Okay, so I'm very optimistic here that we will push this to very large systems where our theory friends will have a very hard time to do any calculation that tracks every single particle that we have, yeah, in our system. Okay, so thanks for the question. Perhaps just one comment. So in our case, with the atoms right now, yeah, we are working with array or bunches of 1D systems, and typically we intentionally work in a regime where we have about 40 atoms per 1D system. 40, so 20 that has a size, then it's about, since the lattice spacing is lambda over 2, lambda is about a micrometer. So we have a size 40 atoms, roughly 20 microns is the size of this 1D system, yeah? along the long direction. Okay, so but I will not talk about any of that work. I will focus here only on the molecules. Okay, let me see if I can go to. It took away my pointer. Okay, so now let me start gently. Also on this part, let me start with scattering. Yeah, remind you of S-wave scattering, because that's what we want to control in our experiments. Yeah, so two-body scattering at this point. Yeah, so in the low temperature regime, as you all know, it's a single parameter that tells us a lot. In fact, if you go to dipolar scattering, it will be a bit more difficult, yeah. But in the low temperature regime, it's because you have your plane wave and you have your scatterer here somewhere. I hope you can see it in the center of the screen. This little dot is our atom. or scatterer. So it's usually the extent is small with respect to the wavelength of our de Broglie wave. And so then you will have scattering of that that defect. Let me call it a defect. Yeah, so that's S-wave scattering. And since I'm an experimentalist, I like to see analogies somewhere. And perhaps you also like the analogy that I did not too long ago with my kids in a local fish pond. Yeah, so have a look. Yeah, so it turns out I try to do this with waterways often, but what helped here really that you had this shallow water level, and that you could see actually the sunlight create. You hardly see the wave, but you see it on the ground, yeah, because of the focusing of the light. Okay, anyway, so this is my little didactic diversion. Let me go further and talk about S-wave scattering. And then, as you know, in some sense, the scattering length A is a measure for the phase shift of this in the scattering process. Yeah. So first of all, it tells us something about the cross section for identical bosons. It's 8 pi times a squared in the low temperature limits, and it has a sign. It is it affects the interaction in a Bose-Einstein condensate. It sets the stability, and as you all know, for rubidium 87, one of the workhorses in the field, this A is on the order of 100 Bohr radii. In fact, that's the generic value that you expect. The so-called van der Waals length is on that order. Yeah. So that brings me to length scales. There's the length scale of the chemical bond, usually below a nanometer for simple systems. Yeah. The van der Waals length is on the order of few tens to 100 Bohr radii. Depending certainly on the mass and the precise value of the C6 coefficient. The scattering length then is, let's say, 100 Bohr radii, but it can be tunable in many cases. We come back to this. Yeah, this is actually why I'm doing this part here, because you can change it and you can play with it. The interparticle spacing is usually large with respect to that. And so we are always in a dilute limit in some sense. Trap size is even larger than that usually, not necessarily if you do confinement in a lattice, then we are not separating that anymore, and then interesting physics certainly happen. And the de Broglie wavelength at typical temperatures, low temperatures, is on the order of a micrometer for, I think I put in here, typical temperature of a microkelvin. Yeah. So as you know, quite often interesting physics happens when these length scale compete, but the way I listed them now here, they are sort of all separated. Yeah. And that makes things sometimes quite easy. Yeah. So where does this all come from, this scattering process? Well, we don't have a delta function potential, but and I'm sure you're aware of this nice review here by John Weiner. We have a situation where we have atoms coming in, scattering on these hyperfine branches. In the end, what's behind it is certainly the hyperfine interaction that then turns into this covalent bond here with singlet and triplet states. And in fact, our goal will be to come from this hyperfine branch for some molecule all the way down to the ground state of this singlet potential. Yeah, so that's well known, yeah, and that's behind of all the scattering. These are the potentials for scattering. This shows a comic for the wave function. Yeah, it's the scattering wave function here at some 1 microkelvin roughly, plot taken from this review, where you have the sine wave, and then this is modified close to the origin, and then depending on the specifics of your atom and the bound states. Yeah, we'll come to that in a second. There is a certain value at the origin that can be 0. In many cases, it's positive, but it can also be negative. Yeah. So certainly the question is, can you play with this? Yeah, can you do something about this? Yeah, can you modify the scattering length? And if you take your favorite quantum mechanics textbook or this lecture here from Jean Dalibard with the square well potential, you know how to solve it. That's elementary physics. And you will actually, as a function of, in this case, of B, yeah, and the depth, the square root of K naught is the depth, as here in the figure of this potential, you will get what we know as scattering resonances, yeah. So you change either the depth or you change the extent of your potential, of your square well potential, and you will get resonances. And this is well known why this happens. Whenever a bound state pops up or goes through threshold, you have a resonance. Yeah, so I'm sure you've done this. Certainly this looks nice, but how do you do this? Yeah. In any real experiment. Yeah. So in real life, neither B nor the depth can be tuned. So go back. I don't go back now to the previous van der Waals potentials that are covalent so potentials that I just showed you, and you will see that you cannot do this. Yeah, but you can do a trick. Yeah, and the trick is known as a Flashback resonance, known from nuclear scattering, is where you have more than just one channel. Yeah, just one, not one well, but two wells, a second channel, and you in fact couple from your incident channel on which you scatter. I assume now we scatter here, as indicated in this picture. You couple onto this bound state. And then you can, in fact, mimic the situation that you change the binding energy of that bound state. Yeah. So what do you need for that? You need two things. You need that this bound state differs in magnetic moment, because it's usually done by the Zeeman effect, this shift. And you need the coupling that I've indicated here by this dashed arrows, yeah, in this comic. Now, this is well known, and this gives rise to a resonance of this type as shown down here. The scattering length as a function of magnetic field diverges at a specific value of the scattering field. So away from the resonance where you have some background scattering length, you have some characteristic that's dispersive, I call it, shape with some strength that's all lumped into the delta, the width of this resonance. Yeah, so this is in principle very nice. Yeah, so this is the situation here. Again, there's just this comic that I just drew on the other side. Here's a picture from this nice review paper from my colleagues, from my colleague Rudi Grimm here in Innsbruck in part. And delta is this zero offset here, indicated here on this plot. Yeah, so that's the generic situation. And I don't go into the details what actually gives rise to this coupling. Yeah, so this is a hyperfine interaction, but it can also be some higher order process. Yeah, and I will just mention the result of that. I will not bore you with any of the Hamiltonians. So now, what does this bring to us? Yeah, so this is my comic. Yeah, with this bound state here in this case below threshold. Let's assume the coupling is sufficiently weak so that there's not too much mixing initially, but basically this looks like the situation that you have one bound state that you can now tune across resonance, yeah, by changing the energy of these two channels relative to each other. Yeah, and this is done usually by means of applied magnetic fields, because it's the Zeeman effect that shifts the energies. So now, so this is actually quite nice. What I just said earlier is possible. Yeah, you can in fact change, tune your bound states through threshold. Yeah. So what's the binding energy of that last bound state in the limit where the scattering length is larger than the van der Waals length? So sufficiently close to resonance. This is a very good approximation that you find in any good quantum mechanics textbook, namely that the binding energy scales as the inverse of the square of the scattering length. Yeah, and certainly I wouldn't be talking about this. We are lucky in our field because these resonances are scarce. Yeah, they happen every once in a while for a typical atom, and it's not a dense forest of resonance, but we have every once in a while, we have one of these hyperfine states that for some other channels come to threshold and cause a resonance. Yeah, the situation is already a bit more involved if you take dipolar atoms. So this is a summary of this Flashback resonance situation. Top is this scattering length as a function of relative magnetic field, and below is the binding energy of the state. Near the resonance, you have this quadratic turnover, but away from the resonance, whatever happens. Yeah, it can look wild. In most cases, it's more or less linear scaling as a function of the magnetic field. Yeah, so these are the formulas. And away from the resonance with some differential magnetic moment, you have a typical linear shift, and this is the zoom in the resonance, and certainly near the resonance. And you can correct and be more precise at what I do here. Yeah. Okay. So that's what we want to control. Yeah. Via the binding energy, we control the scattering length, or vice versa, as you can view it. And in fact, this scattering length also here has a very nice geometric interpretation. In this limit of large scattering length, the size of the dimer is actually A/2. Yeah, so this is actually quite nice and very simple. Yeah, we call this a quantum Halo state. So okay, so now let me plot this actually as a function of 1/A. So B minus B naught effectively proportional 1/A. So it looks like this parabola that goes down here, and this is the two-body physics of this weakly bound state, of that Halo state. And be reminded, there's certainly many other two-body bound states nearby, or not too far away, and they exist. Yeah, that's a nuisance. Yeah, in some cases, and Johannes Hecker-Denschlag will talk about this more. He has really nice results on probing this, but it's a nuisance, but it's also a nice feature sometimes. Yeah. So let me just briefly highlight some of these Flashback resonances that we have in the field. One of the very prominent ones is here shown for lithium 6 fermionic lithium, between these lowest lying hyperfine states in the Paschen-Bach regime. Yeah, so in the field of already a few hundred Gauss, and there's a resonance at around 8. If I remember right, 830 Gauss, very prominent resonance, very strong resonance, allowing to create molecules, but also allowing us or our colleagues to go over the side where there's no molecular state, yeah, on the right, but still being able to observe pairing, BCS type pairing. And so let me go back. Here's the situation of this on the right here. We don't have any bound state. Yeah. But still, we can do interesting many-body physics there. And I'm sure we'll hear a bit more about this in the school. Yeah. So here's the second example of a very nice situation that we love in Innsbruck. That's the case of cesium. So bosonic cesium, there is only one cesium isotope that can be trapped in the lab, cesium-133, the famous one. And there are actually in the range from 0 to 1,000 Gauss, there are essentially 3 resonances. One that is basically at negative fields, but it has its effect on the positive side here, plus 2 resonances at about 550 and 800 Gauss. So that's the situation for cesium. Please ignore the vertical line at the pole of resonance. Yeah, so this is for us irrelevant here. It just indicates where the pole is. Yeah, but what I would like to say is that the cesium scattering length on average, this is done by me by hand, is large. Yeah, so if you take the cesium atom in the lab, you will see that on average, the cesium scattering length is 2,000 Bohr radii, and that has drastic consequences. So one has to work, I already say it here, around the zero crossing here at low fields or at one of the other zero crossings, but it's hard to work at very high values for the scattering length. Okay, so this is the run for cesium, and I should say this neglects higher order resonances. So this is just the so-called S-wave resonances, yeah, where the molecule is that couples to threshold is in an S state. Here the situation is a bit more complicated. This is now the case that we will turn to later. That's partially why I'm introducing all this. This is the situation for rubidium cesium. So you see top the scattering length between, so this is now the interspecies scattering length between specific spin states of cesium, cesium and rubidium. I don't go into details here at this point. At top is the scattering length, and bottom are the bound states. Yeah, so this is the situation for a realistic molecule. Yeah, so let me go back. This was our comic. Yeah, our simple situation. Yeah, one resonance, and the world otherwise is easy. Yeah, so this is a realistic situation. With all the bound states, in this case, higher order states also, and the zoo of resonances, effectively starting useful resonances start at about 180 Gauss and then go beyond to a few hundred Gauss. And I can already say at this point, the resonance that we will be interested in later is this resonance here around 350 Gauss at this point. Yeah, this one S resonance, it turns out. Yeah. Okay, that's rubidium cesium. Just for the record, this field of Flashback resonances in cold atom physics has now been around for 20 years. Started with the work of the Wolfgang Catalyst group on sodium, observing a Flashback resonance here at around 900 Gauss in an atomic condensate of sodium. And in this particular case, they saw loss, and they saw excess energy, and saw this excess energy in the expansion of their cloud. And at that time, details of what was going on were not yet, I have to say, not yet understood. Yeah, this only happened, actually, starting with such work, it actually happened then afterwards. So this is two-body, yeah. Let's now divert a little bit and talk about three-body, yeah. As I said earlier, we are lucky that boson-Einstein condensates are weakly interacting. They are certainly just super cool, yeah. And at those temperatures of a boson-Einstein condensate, any metal is rock solid, yeah, evidently. So this only works because we have a dilute gas, and the process where three atoms meet and then start to cluster up is rather unlikely. Yeah? And it now could have been that we are all unlucky. We wouldn't be talking about this here now if these rates were just a factor of 10 or so rate coefficients. I'll come back to that in a second, what I mean by that. If they were just a factor of 10 or 20 or so worse, then we all would have a problem. Yeah. So what I'm talking about here is the process of three-body recombination, where three particles meet and they actually start populating. Two of them form a molecule with this binding energy, and all three partners in this comic here leave and take away a fraction of the binding energy, as indicated here. So this is a severe problem in principle, and it could have been disastrous. It turns out, no, it's not disastrous. And one can learn a lot about this. But one can then ask again the question later, what this process, how this process happens for molecules. Yeah? So we are talking about atoms here, the simple situation, and later we talk about molecules. Yeah. So in an atom trap, this leads to particle loss. With this, it leads to what we know as anti-evaporation, because it happens where the particles are densest and where the temperature is effectively the lowest, and that actually leads to usually it leads to heating, yeah, loss and heating, yeah, and it's not very much desired in a boson-Einstein condensate, yeah. So now let's look at the situation where we add a third particle, yeah. Coming back to my situation here with the parabolic two-body bound state below threshold. On the right, scattering is positive. On the left, the scattering is negative. But what I've done now, I've added a third particle to this. Yeah. So what are the states associated with this situation? Yeah. As I indicated just a moment ago, what can happen is that upon a collision, you can populate the dimer state on the positive side, and even on the negative side, you could populate some lower lying dimer states. Yeah. And that can be not so useful, yeah. Apart from certainly having interesting physics, but for in the many-body context, we don't want that. So how do we quantify this? Well, we quantify this three-body scattering process in the simplest case without assuming any temperature changes and so on by the simple rate equation for the density with this rate equation coefficient L3. This L3 in this simple way gives us already a loss rate, approximate loss rate. Yeah. So the typical values for this L3 rate coefficient are these values that I'm giving here on the right, 10 to the 28, 10 to the minus 28 to 10 to the minus 30 cubic centimeters per second. We like cubic centimeters per second because we can immediately plug in our typical densities, BEC densities, 10 to the 13 atoms per cubic centimeters. And when you plug that in, you will see lifetimes, or 10 to the 14, then lifetimes are not infinite anymore, right? So they are finite, limited to that. So the first question after measuring this in the lab is, can one calculate L3? Yeah, and it turns out yes. And there's been a long endeavor on trying to do this at the various levels of sophistication. It turned out the first calculations were in the limit of large positive scattering length. And this goes back to this work by Peter Fedichev and collaborators in the mid-90s, where this L3 coefficient was proposed to scale with the fourth power of the scattering length. And that already tells us, well, that's not too good, yeah, because that increasing your scattering length from 100 Bohr radii, like rubidium, to 2000, like in cesium, a factor of 20, increases this by a factor of 80,000, yeah, 20 to the fourth power, yeah. So that's a big number and increase, yeah. Okay. That's so an interesting scaling, and this was derived by basically dimensional analysis with proper prefactor h bar over m. And what actually at that time was not clear, what is this, the prefactor, constant prefactor, c here being in this case 3.9. What is this prefactor? I have to say a factor of 3 was taken out because when a collision happens, it was assumed that all 3 particles get lost, and so it makes sense to add a 3 here. So what is this factor C? And does it show some additional structure when you factor out a to the 4 scaling? And actually, you can plug in a number for rubidium, and you get this number down here for this L3. Yeah, so it reasonably agrees with what you measure in the lab. So after this work, various of our theory colleagues found out that this factor C is actually not really constant. For positive A, it actually oscillates with an upper limit that is actually 70. Yeah, so not 4, but 3.9, but 70. Yeah. And it turned out that calculating this L3 in the general case is non-trivial. If you take this L3 for not a homonuclear situation where you have 2 species, rubidium and cesium, is actually something that is very complicated even nowadays. Yeah. So I'm showing you some data from our lab long time ago, yeah, where we actually looked at this L3 coefficient. In fact, here we look at the 4th root because it's nicer to plot. And we call it row 3. We call it a row recombination length. And what we see on the positive side here, when you do 4th root here, you get essentially a linear scaling apart from small deviations that I can talk about later. But we see for negative scattering length, we see actually a drastic deviation from this A to the 4 scaling. So it tells us that this prefactor C of A that I introduced earlier, yeah, this one here, for negative A is actually strongly modulated, yeah. So what's happening here? And here are 2 data sets with a little hump for 200 nanokelvin, with a big hump for 10 nanokelvin. The red line is some simple theory that I will give a little later. So what's actually happening here? Yeah. So, but just for the record, the 3-body loss rate goes through the roof. Yeah. So by tuning your magnetic field from here to here, so here I'm plotting this as a function of the scattering length, but it turns out this is just a few Gauss. Yeah, from here to here. Yeah, about 10 Gauss. the three-body loss coefficient for cesium goes from this value, increases by 6 orders of magnitude. Yeah. So show me an example of a magnetic field effect where by tuning 10 Gauss you get a change of 6 order of magnitudes. It's rare, certainly. Yeah. I mean, you have to go through a phase transition to see that such an effect, I would claim. Yeah. So what's happening here? And in fact, here also there's some modulations, yeah, that I will not go into details here now today, yeah, but I would just want to mention that, and I will give you a formula later, yeah. So there is some deviation from this linear scaling for the fourth root here. So what's actually happening? I'm going back to my two-body situation here with this bound state. In fact, if you take 3 particles, it turns out there are novel states, 3-body bound states. They are actually known as Efimov states, yeah. And there's in fact an infinite series to ever weakening binding energy, yeah. So there's a ground state Efimov state, and then there are actually more with an actually with an interesting scaling, yeah. This product scaling, yeah. So a factor of 22.7, and I think we saw it already on the previous page. This 22.7 is actually basically a universal number, yeah. So but before I go into the details where this number comes from, is in fact what we were observing is this intersection point of this Efimov state hitting threshold. Here at this point, at a specific value of the magnetic field or a specific value for the scattering length, and causing this monstrous resonance. And in principle, there should also be a resonance here on the right where the Efimov states hits the dimer atom threshold. So where do they come from? Just very quickly. It's not the essence of my talk, certainly. Just for those who want to know, one can write down an effective radial equation for 3 particles interacting in the regime of where R is smaller than the scattering length and larger than the extent of the potential for the so-called hyperradius. And it turns out that in this one gets a 1 over R squared potential, and the bound states, very peculiar, and this 1 over R squared potentials are actually these Efimov states. And the scaling, they have this geometric scaling, and the scaling actually is because of e to the pi with S naught being almost unity, this factor up here. And that gives a binding energy change by a factor of more than 500 from one state to the other. And with this one actually can already start counting how many Efimov states there are because of this exponential scaling, and details are found in this nice review here. So that gives rise to this modulation of C, yeah, and this, the fact that we have this one R squared potential that's actually well known from basic quantum mechanics, yeah, actually gives for the positive side this log cosine dependence of this A. So there is just let me walk you through this. It's very simple. You have a cosine dependence with a log dependence on the scattering length with some phase, yeah, I call it lambda star. And then some width parameter, how strongly this is actually modulated, this cosine, and I call it eta. Yeah, this is actually, turns out this is the recombination rate into the shallow dimer that I just discussed. And there's also a conversion to loss into the deeply bound states, and that's actually that contribution. So that gives rise to modulation for positive A, and the maximum is here about 70 or so. But for negative A, this is actually 1 over that dependence here and shown here, yeah? So you have again a width parameter, but then you have this 1 over sine squared of log of A, and that gives rise to these drastic resonances in the 0 temperature limit. And that's actually, that's what we call these Efimov resonances, yeah. Okay, let me close this, yeah, but in the back, this is always in the background. When we have particles interacting with each other, Efimov physics and a drastic enhancement of the 3-body loss rates to be kept in mind, yeah. So these Efimov states appear as resonant interactions for strong, for large scattering length. There's in principle an infinite series and even higher order resonant Efimov states have been seen. Interestingly, they allow us, the Efimov states can basically be derived analytically. That's actually Efimov's realization. So the three-body problem has in mechanics an analytic solution. They come from this 1/r² potential, lead to this exponential scaling of states. Then that leads to this log periodic modulation of the loss rates for this as a function of the scattering length. And that's for positive and negative, and with pronounced resonance for negative A. And then actually one can even say more about this phase that I've not talked about, this phase so of these oscillations. And in fact, that we think we sorted out some years ago, 10 years ago, but I don't go into details here. But it turns out that for certain potentials, one can make precise statements. What's a bit more complicated is how wide are these resonances, yeah, and that depends on the availability of bound states below, and there it's actually difficult to say something because that's depends on the specifics. And if you want to read some more, actually the second triatomic resonance was observed in Rudi Grimm's team some years ago. Okay, now let me see how time is doing. I think I have a few more minutes. So this closes this divergence. Now let me come to the dimers, back to the dimers, yeah.
5 minutes.
5 minutes, yeah, I'm doing fine, yeah. And I see there is a chat question. Let me open this up.
There are a few questions. Shall I read it?
Okay, how the potential of F, let me read the second one first, become 1/r². Well, you have to do this very, that's a good question. Yeah, I like it. Yeah, wonderful. You have to do this sort of, I call it Born-Oppenheimer type approximation when you treat the three-body problem. Yeah, you have to average out all the angular degrees of freedom and just then discuss the dependence on the hyperradius. And I think this is totally uncontrolled, this approximation. Efimov saw it, probably had enough intuition, but you have to do this. Born-Oppenheimer usually works because you have light electrons and heavy nuclei. Here we don't have nothing, there's nothing light here, yeah? But it still works to some extent. And then it turns out, and you have to do the math to get the 1/r² potential. And that's actually the big thing that Efimov did. So, okay, I could not fully answer that question, but it's actually a wonderful question, yeah? So can you comment on the spinor nature of alkali gases? Okay, so if yeah, this is a little bit off topic, yeah, we'll see whether this will be discussed further. When you have a spinor system, yeah, when you have, so that means basically you have the atoms being in different spin states coherently at the same time, coherently or non-coherently. You have usually slightly different scattering lengths, and in fact, for cesium, I think they're vastly different depending on the spin state. And I think with cesium, we have nothing done really spinor, but I have to be careful. Actually, we have done something, but I cannot, because of lack of time, talk about this. In general, this is a separate story, and I don't think I have the time to talk about this here. Yeah. Okay, so sorry for that. That would be something to talk about also with some of the experts who do this spinor or spinor physics with ultra-cold gases. Yeah, this has been done with rubidium, for example, with sodium, and I can, for example, highlight some very good work from Dan Stamper-Kern in Berkeley on spinor BCs. Okay, so let me turn to the dimer molecules. Yeah, if it allows me to turn. Okay, so why ultra-cold molecules? Let me back up one more time, yeah? Beyond what we said earlier, here are our favorite dimers, and certainly it's not just molecular BEC, dipolar quantum gases, perhaps some quantum simulation with that, yeah? Perhaps going in a regime where we can have long-range interactions in a layer where perhaps we can simulate high-temperature superconductivity. Well, I don't know. I have no idea whether this works. Nobody knows actually, yeah. But there are certainly other motivations that I should briefly mention, yeah. Ultra-cold chemistry, and we'll hear about this a bit later on. Fundamental physics, yeah. Preparing samples of molecules at low temperatures to be able to do spectroscopy with very high resolutions. Yeah, for example, to search for an electron dipole moment or to look for time variation of the electron to proton mass ratio. And here, this iconic picture from Dave DeMille, quantum processing with dipoles that you switch on and off and that you let talk to each other. Admittedly, a bit more complicated than for ions in an ion trap, because ions in an ion trap, as you know, with a laser addressing, you can make every ion talk to every other ion in that chain. That's not so easy with dipolar molecules because they only talk to the neighbor. Okay, good. Okay, that's sort of a motivation, yeah. And let me talk about rubidium cesium here. It has a dipole moment of 1.27 dBi, and so you to get a hold of that, you have to fully polarize the molecule by an electric field that's on the order of a few kilovolts. And we'll hear about this from Juni tomorrow, how far you can polarize KRB until you run into problems. But I think they can do up to about 0.2 dBi or so, or 0.3. I forgot the exact number. Generally speaking, the dipole-dipole interaction is written down here in this Hamiltonian. Yeah, this is sort of the Hamiltonian without going to second quantization. Yeah, the very basic one. Yeah, it scales favorably with the inverse fine structure constant. So in contrast to the magnetic dipole. So that's why this is interesting. Admittedly, I've said this immediately. It's much easier to cool an atom, yeah, than a molecule. Yeah, and so we'll see from Tillman. We see more about this. Okay, so where are as an outlook for tomorrow? Yeah, where are the interesting experiments on this? Yeah, and various places. I've mentioned Junyi. We are working on rubidium cesium in Innsbruck, also on KCS and other places. And also I will briefly, if I have time, talk about our homonuclear endeavor, because that we learned a lot trying to control homonuclear cesium. Okay, so I think my time's up, yeah? So what we will be talking to, let me take slide as a motivation for tomorrow, yeah? So the plan is how to take an atom pair in the trap, in the lattice trap, to be more specific, with a distance of typically 50 microns, all the way to the ground state, where the size is 100 times smaller. Yeah, so you have to reduce that internuclear distance, yeah, and at this point remove the binding energy of this molecule without heating the sample. Yeah, so that's what we will be talking about partially tomorrow, and certainly the first the bottleneck that I already mentioned is creating that atom pair in the first place. Yeah, here indicated just by 2 red dots, but it could be now any atom pair. Okay. I think, Bora, you have to tell me. Yeah, I'm thinking it's up.
Yeah. Yes, your time is up. There are a couple of questions. So, so first one is, if move states work for A tends to infinity, what about if A is small?
Yeah, so it turns out, so the Efimov states appear in this resonant limit of A being very, very large. Yeah. So if you had a zero range interaction potential, but with infinite binding energy, you can even have Efimov states all the way to negative binding energy. But it turns out Efimov states, there's a lowest lying Efimov states, and then you have only higher lying Efimov states. So it's cut off. And they typically appear around when the scattering length is on the order of a few times the van der Waals length. Yeah, let's say 10 times. Then you expect the first Efimov state to pop up, and then as you increase A, you will get more and more of these Efimov states, but the scaling, certainly the binding energy scaling, is not very favorable. So you can actually look at the size of this Efimov state, yeah. So already the second or third Efimov state will already crash your trap, yeah, because they are too big.
Okay, and so then the next question is, can you find Efimov state in fermionic species?
Yes, there is Efimov states, so it's not in identical fermions, but with different spin states. Yeah, in fact, there's been quite some work on seeing Efimov states with where the constituents are fermions. Yeah, I should mention, well, the various groups. I don't want to say too much. For example, I think one group is at Georgia Tech, another group in Heidelberg. So there's been quite some work with fermionic atoms. Yeah. And I see there's a question on, can you
think of radioactive elements such as radium as ultracold molecule?
Yeah, I specifically haven't thought about radium, but a good candidate, for sure, a very interesting candidate would be cesium 134, I believe. Yeah, I always forget whether it's 142 or 34. It's a fermion, very heavy fermion, yeah, and it's not that bad. It can actually be made in a reactor, and it's not very badly radioactive. I think it's 134, yeah. And that would be nice. And I've briefly thought about that, whether we could do it. Well, our friends in Vienna, they have a reactor, and they could make it. But you would have to have your source, the source and your experiment next. I think it would be another fermion. As you all know, we don't have that many fermions in the field. Yeah, I mean, rubidium there's no fermion that can be used. So there's lithium and potassium. They have fermionic isotopes, and then the elements like erbium or rhodium or strontium have fermionic isotopes. But so they're not. There's an abundance of bosons, but not that many fermions. With radium, certainly, I have no idea whether there's any chance of doing anything with this. Yeah, but we've certainly not carried that any further, and there are plenty of things to do with the present fermions, as we will see it during the school.
So is there any more question?
So are there efforts to trap the Efimov trimers? Yeah, good question. Well, the lifetime is rather short. Yeah, so the resonance width sets is essentially associated with a lifetime. So basically, these Efimov trimers are reaction channels, to be honest. Yeah. So in the case of, they will actually mediate the production of a lower lying dimer state and release a lot of binding energy. So that's basically a decay channel. So in our case, we are the lifetime would be rather short. It's less than a millisecond. I'm not saying that this is not possible, and we've never gone any further, I have to say. My plan is to pick this up a little bit, perhaps at some point. In particular, perhaps the next Efimov state is even a bit more stable, just by Frank Condon arguments, and perhaps then one has a chance to stabilize that. The group in Heidelberg by Selim Joachim, if I remember right, in fact, working with fermionic constituents, they actually even did some radio frequency spectroscopy on the binding energy some while ago. So it's, I don't know, 5-6 years ago or so. So there is something to do, yeah. And in fact, an interesting question is what happens with these Efimov systems when you really try to trap them and confine them, in particular in 2D or in 1D, and how this crossover from the 3D physics to 1D physics happens, and whether Efimov physics still exists in 1D. As far as I know, our theory friends tell us, strictly speaking, in 1D there are no Efimov states. But yeah, I would like to see the transition as you try to catch them in the lattice.
Okay, so with that, I would like to give it back to the organizer. Thanks a lot, Christoph. Professor Nägerl will present again the lectures tomorrow at the same time. So thanks a lot for today.